Okay, so welcome everyone. Uh, can everybody hear me in the WebEx universe?
Yes.
Oh, Cortana heard me too, or whatever that is. Okay, great. So welcome, Shamsha Rashid. Welcome back, Michael, Jordan, and Christina, and everyone else is here. Uh, okay, so let's get started. Um, just let's see. Okay, so. The first time, I haven't graded the first homework assignment yet, so I'll get that graded before next time. I was a little backed up on another class, but so yeah, I know it's been a while. It's been a while. I'm historically a pretty nice grader, so as long as you mostly lose points for just not doing things. So if you made a good attempt, you probably got most of the points. If you didn't do it all, then you might have lost points. That's usually how it goes. That's 200 points in this SAT, right? Yeah. Well, it is that's probably like a valid way to give points because like if you mess that up, then the whole thing gets screwed up, right? If you know, so the most important thing is categorizing the grade and getting it to the center. So yeah, that's important. Okay, so I'll get that first assignment graded by next time, and let me know if you have any questions on that. No, yeah. So we do have another homework today, but we'll get to that. And this is week 5. So what I want to do this week is transition into multiple regression. And so that means that we're going to not have just one X variable. We can have 2 or 3 or more, as many as you want. You can have 20. We're not going to do things in 20, but I have seen cases where there's a number of variables that you can kind of, and so if you have the data for something, and let's say you're looking to explain some variable, you could gather as many variables as you want and kind of go through them and kind of pick and choose by running some analysis. But for starting out, I'll tell you what to define and run, and then we'll go from there. But at some point, you should be able to gather your own data, gather your own variables, and determine which one should go in and which one should go out. Yes. This part? Oh yeah. The Excel part, right? Okay, sure. Okay. Yeah. Okay, we're gonna do. That's all right. We're gonna do PowerPoint first. So yeah. All right. So we got. That's all right. Okay. So I put another PowerPoint, and again, I don't want to freak anyone out, but we'll go through a couple things. Some things we haven't got to yet, but some things we will. So just gonna give you a few, slideshows or to make it official. So let's open up lecture 2. And some of this we've actually already covered. Some of it we will not cover yet, but I just kind of want to highlight some things. So we've learned the least squares estimator, which is to pick a linear line that best explains the the data points and try to get the best line by minimizing the sum of the squared errors. Okay, and this was seen last time, but it should be a little less scary this time because it's just representing different possible variables that can affect y. So we focused on just x1 thus far, but we can add more x variables, which we're going to do today. And so this is just the general form. You don't have to write this. It's not as scary as it looks. It's just representing the fact that your dependent variable is explained by some intercept, and then the beta is the linear effect of each x variable, if there is any, on the y variable. And it's possible we could have an extra x variable or a third, or so on. And so each time you add another variable in a linear fashion. You're just looking at, it's similar to what we did with the one, but it's often likely that there's more than one variable that affects the y variable. And if so, you want to use that in your analysis. Okay? So each beta is the effect of that x variable on y, and that's it. Like there could be one thing, there could be two things, there could be up to k number of things, which is just a general term for. And then the little u or whatever you want to call that little symbol is the error or the unexplained portion. So we want to explain as much as we can, but there's always some part that can't be explained, and the part that we can't explain is represented by the error term. Okay, good so far? Okay. Okay, and we actually already did this. I actually showed you manually how to do the t-statistic, although you didn't have to do that. We manually calculated the intercept and the betas, remember last time? And then we did tests where we looked at the t-stat for our x variable. And then the next part is we compared it to some critical value looking at the t-table. And then by doing that, we could test if the variable is significant or not. So this is just a written way of describing what we already did by looking at the t-stat, comparing it to the table, and determining if the variable is significant. Okay, and then I gave you some, background math on manually calculating these things. The alpha, the beta, the t-stat, and then the important thing is knowing the basics of where that comes from and then how to use it in interpretation. Okay, so and it says here, like, just want to point out that sometimes like a textbook will say we want to use a 5% level, and so that means 95%. So you can either say like a 5% or 95%, but it's kind of the same thing. So I usually like to stick with the 90%, 95% because it makes more sense to me. But if you see a 5%, they're just reversing it and saying that the unexplained part is the 5%, but you're explaining 95%. So in this context, significance level of 5% would be the same as 95%. Okay. Now, I like this little graph. I don't think I've showed it to you before, but this is your um, for your hypothesis test, the t-stat. This is kind of your acceptance region and your rejection region. And so essentially what you're doing is uh, if your t-stat and your coefficient and your um, t-values follow kind of a normal distribution, then this is kind of what you're interpreting. So you're basically saying that I'm 95% sure I'm in this region. There is some possibility that I messed something up or missed something in these outer portions, like this region or this region, but this is the region you're 95% certain about. But there is a chance, there's always a chance that there was something happened in the data, something was not the right correlation. And so the region which you're unsure about is these extreme areas to the right and the left. Um, Not necessarily. No, good question, but so no, that's not the error. This is the region in which your um, conclusion could be wrong. So when you like when you talk about the coefficient, like you're interpreting, uh, I don't know, you're saying that when it gets colder or when there's more snow, it's colder, and your interpretation was like, yours was like however many snowballs lead to more cold, so if it snows more, like if it snows an extra foot, then it's, or sorry, if it is colder by like 1 degree, then it snows an extra foot. So that interpretation, so there's basically a 5% chance that that is wrong, that the data was, yeah. So it's just saying that you're pretty sure you're right, but in stats, you have to always make a statement and saying like, there is a chance, a small chance that I didn't get it right. Okay. Now, we already did this. You got the t-value from Excel. You looked if it was greater than the critical t from the table, and then you determined if the variable was significant or not. And so I don't think we've come to a case where it wasn't significant yet, but in the future, we're going to get to that point. And if it's not, you can either note that or you can take it out of the model because it's not adding things. Okay, so dummy variables or binary variables, we're not going to look at today, but we're going to probably look at these next time or the week after. And these are, I like to do these later on because they're a little bit trickier, but these are like categorical variables. So if you wanted to note if someone is a smoker or non-smoker, if they're, um, if they're, whoops, sorry, Republican, Democrat, if they're in school, out of school, or if they're, in the public sector or in the private sector. So if you want to note just things that are not quantitative, they're categorical, like these things, then you have to model that a bit differently. And essentially, we'll look at some examples, but your data set would show like a column saying like, if this is true, then you put a one, and if it's not true, you put a zero. So if you're familiar with like the uh, pop culture of like binary variables, like looking at everything as ones and zeros, that is this kind of modeling in which if it's true, it's a one. If it's not, it's zero, and you can kind of control it that way. So I'll show you how to model these kind of things, but I just want to introduce them here. But we won't have these until at least next time. Okay, guys, so far? Yeah. No. Okay, we also haven't looked at residual plots, which we'll get to in the future as well. And this is going to look at um, if you look at if that little wide I is the observation of y, and the y has the predicted line. So each time that the y you get from the data set is not on the line, there's an error, right? From distance from the line, like when we had the plot of data with the fitted line, the ones that were farther away from the line had a bigger residual. And so in the future, we're gonna examine those uh, properties or plots and make sure that the properties are make sure they hit a number of qualifications. And if they don't, then there's something biased or kind of incorrect with the interpretation. And for example, let's say that your error terms are showing you some kind of pattern. Like let's say that, and the reason why this is, again, we'll cover more of this later, but the reason why you wouldn't want like yes, the hat is the predicted line, and the non-hat is the actual observation. Yeah. So the distance is how far off the actual observation was from the line. Yes. Okay. And the reason you wouldn't want some things like your, remember we did the correlation. So if you were to do a correlation for these residuals, like the errors, you wouldn't want them to have a correlation or a predictive power with each other because then you're missing something obvious, or not obvious, but you're missing something in the specification that needs to be or re-specified. So there's a number of properties that have to hold in the error terms for you to interpret it in the correct way. So we'll get to those in a bit. Uh, Ignore this for now. Actually, no, don't ignore this. So this is a y variable, and this is the residuals, and each point is showing how far the residual was from the actual. Like if they were exactly equal, like if you predicted it perfectly, it would be zero because there is no difference, right? If this is equal to this, then this is zero. So if you get it right on the line, then it's here. But if you overshoot it or undershoot it, it's here. And so we'll kind of see that what you want your residual plots to look like is just kind of a scatter plot of no correlation and things that are above and below zero. Um, but we'll get to that later. Okay. Now, okay, residual plots, we'll look at those maybe in a couple weeks. Okay, another thing um, we'll get to is another property of the residuals is two big words which might not which you probably haven't heard of, but or maybe you have, but you can get properties called heteroscedasticity and homoscedasticity in your error terms, and you're looking for the essentially the variance to be constant. And so this looks weird, but the reason why you don't want something like this one on top is because that would tell you that as you're adding more observations, then they're getting worse at predicting. So you don't want like bigger observations or future observations to get worse. I mean, it's okay if like some are worse than others, but if it's clearly that you're so this is like uh, whatever 20 and this is 40, and so if you're adding more um, observations and the error term is getting either bigger or smaller, like what I mean by that is the variance, the distance from the line is getting worse and worse and worse, or something like that, then that would tell you that something's misspecified. So what you want, you can assume there's going to be error. You can assume you're not going to hit the line perfectly, but what you want is not perfectly, but you want to have something where each error is about the same as the next one. It can be, it won't be perfect, but if you see something like this where it's like my predictions are getting worse and worse and worse over time, that's something you need to relook at because something's wrong in the specification.
So if we get a kind of diagram like hetero,
Heteroscedasticity.
yeah, that one, that means something's wrong, definitely.
Uh,
So we get something almost
you want homoscedasticity. Yeah,
because it's closer to each other.
yeah, right, exactly. Yeah. So the right, this one's good, this
And
one's
this
bad.
would be some sort of maybe like
But not the line is not the issue. What is the issue is that
close to each other.
the
It would be
spread, yeah, the spread is the same. Yeah, that's the main thing. Okay. So okay. So we'll come back to that. And then we're also going to look at something called outliers or influential observations. And these are things which can skew the results if one or two or more of the observations is extreme. And so if you look at this plot, um, so here's like you're using height to predict weight. Okay. So if you use height to predict weight and you have some observation that's way up here, it's so much different from all the other ones. If you don't have enough other ones, look how much that can skew it. And so if you have something that like look at this is height and this is weight. Here's all their observations, which are in the same kind of region. And then this one's way up here. So this person was very tall, and because of that, the normal predicting power of that observation is way higher than or way different than the others. And so if you leave this person in or this observation, that can skew your results. And so if you look at this plot, um, the black line would be to take that individual out, and the red line would be to keep it in. And you can see that it really skews your
like
height is X and weight is Y. And the point of the picture here is to show you like this one. See how all the points are down here, and this one's way up here. So this one, if you leave it in, can influence or skew the results because it's way out of the normal range. Okay, right?
But then all of them almost same.
So just look at this one here and then this one here. So the ones that have the red lines. So for example, this, or let's see, wait. So this one down here. So this black fitted line doesn't include this one, and this red fitted line does include this one. So see that if you include that outlier, that the fitted line can be skewed up, but that might not be a good representation of these individuals because what's ever going on with this really tall person isn't the same as what's going on with the normal population, right? So if you don't have enough observations, this can influence your results, and you either want to note that or take that individual out, or if you can, get a bunch more observations so it doesn't matter.
So we're talking about that the four observations, four high. So all of them are four. So I cannot give only one of the map, or I can all four is four.
I'm only focusing right now on this one and this one. So the two squares with the red lines. Yeah. And we could look at these ones too because this shows the residuals. So you can see that, like, if this is our fitted line, look how far off that person was from the fitted line. That's how big the error was. So the point of this is to show that when you're doing these analysis, and you can actually, like, there's programs that can check this for you, say like this observation looks like an outlier, or this observation needs to be checked. And if you don't check it, it can misinterpret your results. And so the usual recipe to make sure that there's no uh, outliers is to get tons of observations. But if that's not possible, then you might want to take this person out because they're skewing the results, right? Okay. So again, I'm just highlighting some concepts that are forthcoming. Nothing you have to learn right this second, but okay. So got that. Okay. Another statistical term that might be new is called multicollinearity, and this is when the x variables have a correlation with each other. And so you wanted to have, if you recall, that we were looking for a high correlation between the y variable and the x variable. Remember last time and looking at those? What you don't want, or which can mess up your interpretation, is if the x variables have a correlation with each other. Now, if that's the case, then it's hard to know which variable is, uh, like, let's say, for example, so we'll get to this in a minute for the homework, but let's say that we're looking at this consumer one. Um, and let's say that income, so the model we're going to look at in a minute is going to predict amount charged with both income and housing side, not just one. So let's say that these two are very correlated, which means that when the, which is unlikely, but just for example, let's say that when uh, the household's income goes up, they buy a house with they have more people in the house. Well, maybe it's possible. So let's say that there's a clear upward correlation where if the household size goes up, they have to make more money. Now, if those are very correlated, like they have a correlation of like zero point 0.9, then you won't know if this or this has the right um, interpretation because they're so correlated. So if that's the case, it would be tough to interpret this and this individually because they have a correlation with each other. You don't know which part goes to income and which part goes to housing, right? So something we'll focus on in the future, but it's some when we kind of perfect our regression kit, you want to be able to look at the variables, the x variables, determine if there's a correlation going on, and then figure out what to do with it. Okay? Because if there is a correlation, then your normal interpretation of the x variables is not going to be correct because you don't know which effect is coming here and which effect is coming here. Now, note that if you're only concerned about predicting the y variable, then the correlation of the other ones doesn't matter. But if you're interested in interpreting these variables, then it does matter. So hopefully that wasn't.
Yeah, I got it.
You got it?
It's better.
Yeah.
Which X is better?
Well, so we'll find out. Well, maybe they're. So
Makes sense.
yeah. Well, I guess the point would not be to find out which X is better. It would be to find out, do we need them both? And if so, like, what does that mean? And is there, so you might need them both. So it's possible that these two are both better together at predicting this, but it might also be possible that these two things are very correlated and you have to pick one. You don't know until you look at the numbers. Okay, so that fancy term is for if the x variables are highly correlated with each other, that's called multicollinearity. So you've learned at least three big words, right? Um, heteroskedasticity, homoskedasticity, and multicollinearity, right? So there won't be like a spelling contest, but um,
Well, throw it in there.
throw it in there. Yeah. Okay. So if okay, so we'll come back to that. One more concept, then we'll move on to looking at uh, our first attempt at multiple regression. So final thing, yeah, question. Sure. Yeah. You just have to explain multicollinearity when you come back.
Okay, good.
It's okay.
Okay, you know.
No, 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 just go. No, I want you to please use the restroom if you have to. Yeah. Okay. Um, okay. Everybody good? Remotely, we have a quick bathroom break for.
All right, thank you.
How are you? No, I took the charger, which is why I'm waiting for us when we get to the stuff, so we lose chargers.
Yeah. Okay. Good strategy. So last concept is called spurious regression, And this is when you might find a relationship between two variables that doesn't make sense theoretically, but it shows up in the data. So I think I mentioned this last time, but the whole thing is like uh, correlation doesn't cause correlation isn't causation. And so this little example shows two things that look very correlated from 1970 to 2010 or something. So this is air passengers in Australia, and this is rice production in Guinea. So they have a very high correlation, which might be just a coincidence. But if you were to, present these results, you'd have to have a good reason why you're showing that rice production leads to air passenger travel in Australia or vice versa. So it doesn't make sense to me why this would cause this, even though there's a correlation. So even if you see something like this, it doesn't mean it makes sense in the interpretation. So unless we can think of a reason why rice production leads to more air passengers in a whole different country, then this doesn't matter, right? So unless all these air passengers are going to Guinea to get to buy rice, possibly, but we'd have to know that, right? So yeah, make sure that when you find a correlation that you can validate why there is a correlation. Okay, so again, we're not going to. I just wanted to introduce some things that are forthcoming in the couple weeks. Um, but any questions on this at this point? Not yet. Yes, there will be. Yeah. All right. Let's close that. Let's close that. Okay, and then I have a nice. I'm going to show you a little intro video on multiple regression, and then we'll do some. Then we'll start doing the homework together, and then you can finish it uh, at home as work. Um, okay.
Or you can together.
We'll do at least one. We'll do at least one. I only gave you three. Yeah, they're all equally the same, right? Well, you can pick which one you wanted. Yeah, I mean, there's one we haven't done yet, so these two you've already looked at. Yeah. Okay. So let's watch a quick video. Oh, why is it- All right. We'll come back to this one because this is introducing uh, dummy variables or binary variables, and we'll get to that next time. So in this case, we have uh, specific categories where you're either in this category or this category, and the interpretation is a bit different. So I think that first one is a good start. So why don't we, okay, why don't we open up homework 2 under week 5? Oh yeah, I do. Well, yeah, because it has to be it has to be clear this time. Yeah. Okay. Okay. So for this um, example, or for this homework, sorry, you're gonna have 3 different examples, and each of them you're gonna do a multiple regression. So we're gonna have more than one x variable, and then it'll be somewhat similar to what you did before, but a little bit different. So we'll do at least one example, and then I put some readings, just a couple sections in that online textbook. So you can read the section 2.1 on simple regression, which should be a refresher, and then 3.1 on how multiple regression is a bit different. And if it gets a little, you know, too technical, that's okay. Just kind of read through it, but it'll give you a little background. Okay, so what you're gonna do by next time is do these examples. So for the first one, we can use dataset consumer. Um, so I do. Does the class want me to start with a certain one first? Does it? That one's fine. All right, so let's do consumer, and you'll see that under week 5, you can open up the consumer dataset. Okay. All right, so what we're going to do to start is run a multiple regression in Excel where amount charged is assumed to be a linear function of both income and household size. So there's 2 x variables, income and household size. Okay, so in other words, amount charged is the y variable, and both income and household size are the x variables, and then we'll include these things in our answer. So the first thing we want to do is run the analysis. Okay, so if you go back to consumer, and let's see, if you do data and data analysis and regression, and okay. Okay, so the y range should be the y variable. So if you click on this and choose amount charged, which is C1 to C51. Yes. Yeah. And then the x range, you're going to choose both variables at the same time. So you're going to choose A and B is a range. Yeah, so you click on it. You got it. Okay, and then your range for the x variable should be A1 to B51. So it should include both variables. So if I look to your, and then you want to click the labels box. So Y range is C1 to C51, and X range is A1 to B51. So notice that the X range includes both X variables,
So when you choose both of them, you choose A and B together.
A and B together. Yeah.
That's okay.
And then hit OK. So now you should get something similar, but you should have two variables to interpret. All right, and if I want to just uh, simplify this with um, Home tab, format, format cells, and then number with the comma sign and the two decimals. I can hit OK. Okay, and then you've got your, it didn't work?
Forward. Yes, forward.
Oh, all right, so you choose everything with that triangle up here. Like click on this. See how it's like,
I'm not sure what you meant by that.
I don't get it.
see where there's like the A and the 1, and there's like the thing at the top? Like that? Like this triangle right here?
Yeah.
Control A.
Yes, there you go, Control A. And then Home tab,
Okay.
and then Format, and then Format Cells. All right, and then just change the category to number. Yeah. Okay, and then so just a second, we got and then if you want, I'm just gonna increase the. There we go. Okay, so if you notice, we have uh, an R squared that we can interpret. We have two coefficients that we're going to interpret. We have two t-stats we have to be concerned about. And then this will tell us the right critical t in the chart. One R was there's a R, just one R squared.
One, one I square.
Yeah, just choose the one that says R squared. Yeah. Yeah, good. Oops. Yeah. Okay. Uh, everybody good? Good. Yeah. Okay. So why don't we start with the answer part? So first thing is we're going to write out the equation. So part A is to start with the general equation. and then plug in the coefficients to make it the estimated equation.
The-
Yeah,
Then you might cover it. Right? The X, there's two X's. Is it okay? Label them like X1 and X2.
sure.
That way,
You can,
it just helps discern like all the information.
yeah, you can do that. Yeah.
Do that at the beginning.
Oh, I see, like we did last time. Yeah.
Yeah, yeah.
Yeah. Yeah, you can do that. There's two coefficients. Yeah. All right. No, not yet. Oh well. Okay, so why don't we start under part A? Oops. Let's write out like the general equation we're trying to estimate, and then we'll put in the coefficients in a second. So we're trying to estimate um, amount charged. This is okay, and like you said, this is the y variable, which is a function of some intercept, and I'll just call this b0 for like the intercept, and then plus, um, or maybe like you can do it if you don't have to do this, but I'm just if you want to do like the subscript, it's under home tab and font and subscript, just to make it look more like the
Oh,
yeah
mapping.
yeah okay, and then let's say we have beta 1 times this will be the effect of income, and then we have plus beta 2 times, and this will be the effect of household size. Okay, and I'm going to put this as a subscript. This there's a shortcut too. This one. Subscript. Okay, so before we did the analysis, we're concerned about seeing if amount charged is affected by both income and or household size, right? Okay, so now we've got estimates for these b's or these betas, right? So now we know that amount charged has been estimated to be a function of the intercept is 1,304.90, right, from the output. So the intercept is the beta 0 or the intercept. And then plus the coefficient for income, which is 33.13, right? Times income. And then finally, plus the coefficient for household size, which is 356.30 times household size. Okay, so all we did here was define the general equation and then plug in our betas from the results. So you plug in this for this for the intercept, this for beta 1, and this for beta 2. Right? Okay, so that's part A, this part here. Okay, so for the other ones, if we don't get to them, you're going to define the equation, And then with the coefficient results, you're going to plug those in for the effects. Okay. Now, part B is let's interpret the R squared. So the R squared equals 0.83. Okay, which means my little arrow. Uh, so same as before, this is about 83% of the variation in amount charged is explained by this multiple regression. Right, so nothing new there. Okay, the t-stat is similar, but now we have two things to check for significance. Okay, so we have a t-stat for income, and we have a t-stat for household size. You can already tell that both are big enough, but just to do the analysis, because uh, we have enough observations, but just to be consistent. So, oops, sorry. Okay, so for the t-stat part, we have um, income, or we have a t-stat. We have income, and we have household size. Okay, so the t-stat for income is 8.35, and the t-stat for household size is 10.73. Okay, right? Yeah, 8.3. Okay. So now what do we do? Or what did we do last time? So we're going to go look at the t-table, and we're going to make sure that these t-stats are bigger than their critical t, and then confirm if they're significant or not, right? So where did I put the t-table? Week 2? No, I don't like this one. Week 3. Okay, so we are going to look at this for our degrees of freedom, which is observations minus 3, so that's 47. And that means that for 47, we can just do this one. And we want to make sure that those numbers are bigger than 2.021. Okay, so we don't have to take the negatives. We know that this is bigger than that, and this is also bigger. And so they're both going to be the same because they're both in the same equation. You have the same number of observations, right? So 8.23, 8.35 is bigger than 2.021. So that tells us that this variable is statistically significant at the 95% confidence level, right? And the same with this one.
Like exactly. Percent. Forward.
Right, there's two of them.
Open iron.
No, I just,
Four.
yeah, it's the same.
Okay.
I just sometimes, yeah. It sounds more fancy. Okay. All right. So, next part, make it so this is to interpret the coefficients. All right. So this time you have two, and let's see what we got here. Okay, so the first coefficient, or let's, so coefficient, and we got one for income, and we got one for household size. Income is 33.13, and household size is 356.30. Okay. This is like double margins or something. Okay. All right. So the coefficient for each is that, and we have to interpret what those mean in this context. So income. So income is income in thousands of dollars, right? Okay, so this one would be something like if the household's income increases by uh, one, which is $1,000, right? Okay, and the reason why it's 1,000 is because this is in thousands. So 1 unit of this is 1,000. So that's why it's not $1. It's 1,000 because the column is in thousands. Right? Okay, so if the household's income increases by 1,000, we would expect amount charged to increase by, and this is dollars, by $33.13. Okay, so if the household's income increases by 1,000, we'd expect amount charged to increase by $33.13. Okay, right? And then this one is for household size. So this is household size, which is just like, two people, three people, so on. Okay. So how do we interpret this one? 356.3. Yeah, you gotta. Okay, so in this case, we're changing the household size, right? So it would be if the sorry, size of the household increases by one, in this case, it's one person, um, the expected change in amount charged would be 356.30. So basically, each person adds this much to the credit card. Okay, so if the house size of the household increases by one person, the expected change in amount charged would be plus 356. Now, the one thing you want to mention, because this is multiple regression, is that you're interpreting these things individually. And so you don't necessarily have to put this every time, but when you make these interpretations, you're saying this with kind of this statement, holding all other um, variables constant. So that means that, oops, that means that this interpretation is individually for household size and amount charged. If income were to change, then that interpretation might change. So you're interpreting these individual effects, assuming nothing has changed. If something changes, then your interpretation would change. Okay, and you might notice that if you looked at the example from the previous homework, it's likely that the coefficient changed. So we, what did we, which one did we do for the first homework? Amount charged and just, was it, well, I can just do it again, but was it income or was it house? It doesn't matter. Let's do it for, let's say it was for, all right, so don't do this part. I'm just showing it as a reference. So let's say that I looked at just the effect of amount charged and household size. Okay. So let me run that single household. Okay. Thanks. So data analysis. Okay, that's the same. And then this would just be household size. Okay. So if I just did income, or sorry, amount charged as a function of household size, the results were a little bit different, right? Okay. So if you look at the just the household size, um, the coefficient was not the same. It was 356 this time, and if we did just that, it was 404. So if you don't include the other variable, then the interpretation will change if you left something out that was important. And then, so also if you look at this r squared from before, just by adding in uh, income, that went up from 0.5 to 0.8, right? So just using household size would explain about 57%, including both variables, decrease the power of this, but it explained about 30% more. So if you're looking to explain amount charged, then clearly using both is better than using just one. Okay. Okay, so you wrote out the equation, which was this one here. You interpreted the r squared. You did a t-test for significance for both variables, and then you interpreted both variables, and then noting that it's holding all other variables constant because this interpretation or this interpretation assumes that this doesn't change or vice versa. So it's really not that much different, but um, you're looking at multiple things that can affect, and you can't really like, so there's no graph to depict all these things together. You could look at this graph or this graph, but if I were to look at the graph of all these three together, that would be like a separate axis. It would be three-dimensional. Okay. So we won't do it. We're not going to do any like, you know, XYZ graphs here. Okay. So that's for this homework. That's the answer, or that's the full answer. For this one is put the equation in, interpret the r squared, do the significance test, and then interpret the coefficients. Later on, we would do some other analysis by looking at the residuals, looking at the correlations. But just by looking at including them both, it seems like using both explains a lot more than using just one. Okay. So questions on that one? No? Yeah. See, well, because we're building upon what we've already learned, right? Oh,
Never do.
So I have a question. So the second one, movie title. So just I have a couple questions on it.
yeah, sure. Yeah, we'll take. So, do we need a break, or no one else needs a break? Okay. All right. Well, we can probably do another one if you want. Oh, yes. Go ahead.
Okay. Yeah, yeah, I think this is off topic, but I think the highest grossing movie of all time movies in today's standard to include inflation would be Gone with the Wind.
Yeah, I think that's true. Yeah, I think that's always going to hold because given what it made at the time. Yeah. Yes. So, what do we do? Okay. Do we want to do number two or number three?
Whatever it's all right.
Yeah, it's similar.
Then we
Yeah, we could.
do that.
Okay.
Either or, they're the, I mean, process.
The same. Yeah.
All the places need, how to keep the place, like there's only from
Yeah. Well, that's the hardest part. Yeah.
oh
Yeah. So that should be the the challenge. Okay. Well, let's look at number two. All right. So let's open up um, movies 2016 again. Okay, let me. Close this. Actually, let me save this before I trip on the quarters. Okay, there we go. All right, so if we go back to the Blackboard page under week 5, we can open up uh, movies 2016. Okay, so now I think the equation was to use 3 of them. So part 2, using Excel's movie 2016 dataset, run a multiple regression in Excel where total gross sales is assumed to be a linear function of opening gross sales, number of theaters, and weeks in release. So there's 3 different X variables. So total gross sales is Y, and the other variables are X, and we'll do the same thing. The only difference is we have one more to talk about. Okay? So first, we need to define the equation. So we need to get it so the X variables are adjacent. So the thing we can do is just, if you click on the C column and just hit under Home tab the Insert button here a couple times. And then if we just choose the F and G columns,
Okay.
to
No.
F and G. What? Oh.
So what did you do? You click on what to move it over? Click on C a couple of times?
Yeah, so I clicked on the C column, just select the whole thing. Under Home tab, there's an Insert button or icon here. Hey, see that? Insert?
Oh, okay. Got it. Insert.
Yeah, hit that twice. There you go. And then you're gonna cut and paste the F and G section into C and D. So if you choose F and G together, and the shortcut is Control X is copy, or cut, Control X is cut. And if you go to C and D and do Control V, that'll paste it. Control X is copy, Control X is cut, Control V is paste.
Control V.
Control V is in Virginia. Okay, and the reason we did that is because we need to select our X columns together. Okay? All right. So
When you go to the text, yeah.
these 3 are X, and this one's Y. The total gross sales. Yeah, yeah.
Like if you read the description, it says run a multiple regression stuff or total gross sales. Pieces to be a linear function of.
Yeah. Yeah, so we're trying to explain total gross sales with the other things. Okay? So then we want to do the regression with the third. So we would do data. I cut and paste them into C and D. Yeah. If you copy them, you can just delete them. Yeah. Okay, and should make sure you have like everything lined up. Like there should be 100 observations. Should be. Well, with the title. Okay, data tab, data analysis. Same thing, regression. Okay. And then Y range is the E range. E1 to E101.
So this E is the one?
Yes. And then X is
All three of them.
B, C, and D
Got it.
together. B1 to B1 to D101. Okay? So Y range is E1 to E101, and X range is B1 to D101. And then make sure you click labels, and then hit OK. And then you should get results for the 3X variables. Get an error? All right, and then I'll, yeah, with the title. Yeah. What? You're done? Nice. Yeah, see? Yeah, yeah. Yeah, yeah. See, you keep doing it, you'll get it. Yeah, we got opening sales, number of weeks, and then weeks in release. Got it? Yeah, see? Eventually it'll be like a,
Eventually, I was like, okay, they're gonna go through bullshit.
yeah. Well, you won't even have to think about it, you'll just do it. Yeah. All right. So we've got a R squared of 0.9. We've got the residual degrees of freedom of 96. We've got these three t-stats. And we've got, I'll actually highlight the intercept coefficient because we need to include that in the equation, which I didn't do last time. It doesn't make, this is just for visualization. Okay, so we can see that when we get to it, the number of weeks, number of theaters isn't going to have a clear effect. So we're going to have to note that. The other two do, but this one doesn't. But first, let's just right. Well, no, because the t-stats. Yeah, this number doesn't matter, but this number does. Yeah. Yeah, I think it is. So let's start with the equation. Okay, so our multiple regression equation would be that opening, I'm just going to say like opening gross sales, oh, sorry, total gross sales. Okay, is a function of the intercept, or let's write the general part first. Um, beta 1, which is the intercept, sorry, beta 0, which is the intercept, plus beta 1 times opening gross sales, plus beta 2 times number of theaters, and then plus beta 3 times weeks in release. Okay, total gross sales is a function of the intercept plus beta 1 times opening gross sales plus beta 2 times number of theaters plus beta 3 times weeks in release. And then the betas will be replaced by the coefficients. Okay, so let's write that with the numbers. Total gross sales is equal to negative 67.22. So that means the intercept is, well, just put the number in, but it doesn't, the intercept doesn't really have a clear interpretation. Uh, beta 1 is now 2.38. Beta 2 is 0.01. And beta 3 is 4 point, whoops, 4.54. See if I can. Um, just trying to make it fit on the same page. All right, so total gross sales equals negative 67.22 plus 2.38 times opening gross sales plus 0.01 times number of theaters.
Oh, B and C, right?
B1, beta 1, beta 2, and beta 3.
Oh,
Yeah, yeah. So total gross sales is a function of negative 67.22 plus 2.38 times opening gross sales plus 0.01 times number of theaters plus 4.54 times weeks in release. Right? Good. Everybody's good on that? Sees what I'm doing? All right. Uh, now let's do the R square. Okay, R square equals 0.0 0.90. So we explained 90% of the variation in what? Total gross sales. Okay. Part C. So we have a T-stat for opening gross sales for number of theaters and, oops, I put it like the British way, weeks in release.
Say the same thing as this time there was direction. Last time. Direction doesn't matter.
Oh, no, it doesn't matter. I just ran out of room to write that.
Okay.
Yes.
Oh, yeah. Okay.
Yeah, I
I
was,
just wasn't sure.
no, either one's fine, as long as you have this part.
Yeah.
The rest is just a prepositional
Yeah.
phrase. Okay, so let's see. T-stats are 19.58 and 1.31 and 7.60, right? So we gotta find the critical T to compare to, right? So that would be 96 degrees of freedom. And that's gonna be, we'll say here, we'll say 100. We'll round up. Yeah, we'll do 80 then. I'll do, that's,
That's what we talked about.
yeah, I was just, you should have written it down, yeah. Yeah, you're right, you're right. I was gonna cheat. You caught me. Okay. Uh, okay, so 1.990. Oops, why is that? Okay, so 19.58. Better? Yeah. You can't move closer too.
No, no problem.
Oh, I see.
Okay.
Yeah. Well, we can fix the chairs further if you want.
Yeah, but
Okay. No, I'll make it bigger. There you go. Okay. Okay. So 19.58, is that bigger than 1.990? Yes. So that we can say that one is significant at the 95% level. Okay, but finally we got one that was lower than, right? So this, the T-stat for number of theaters is less than the critical. So that one is not significant, right? So this would be not statistically significant. So that means that the the effect of this on the y variable isn't strong enough in the data, and you don't really have to interpret it because there's no clear relationship. So if it's not significant, then in theory, what you would do is probably take it out and run it again. But for the purpose of this exercise, just make a note. And then when we get to the interpretation, you can say you don't have to interpret that one because it's not significant. Okay, but make sure that you do this part because some of the variables aren't strong enough. And I think we confirmed that when we looked at the graph, that there wasn't a clear relationship between number of theaters and total gross sales. But the other one, weeks in release, that one is bigger than 1.990, so that one is significant. Okay, so opening gross sales significant, weeks in release significant, number of theaters not significant, right? Okay. All right, now everyone's favorite part, the interpretation of the coefficients. All right. Let's make sure that, oh, someone. Okay, so coefficient, opening gross sales, number of theaters, and weeks in release. Okay. So this one is 2.38. This one is not significant, but we'll just put it 0.01. And this one is 4.54. Okay. And then let me see if I can fix this. All right, so why don't we start with this one? So remember, opening gross sales is sales in millions, and total gross sales is also in millions. Okay, so what does the 2.38 mean?
If the opening gross sales increases by 1
Yeah, that's it. Yeah, exactly. So if opening gross sales uh, increased by 1, which in this case is 1 million, we'd expect to see that uh, total gross sales had increased by 2.38 million. Okay, why is it, what's wrong with my if? If opening gross sales increased by 1 million, we'd expect to see that total gross sales had increased by 2.38 million, right? Yeah. Yeah. Okay, now this one, because it was not significant, you don't you can just you're not going to interpret it, and you'll just make a note. So because this one's not significant, you would say like something like not statistically significant and uh, interpretation invalid or something like that. Okay, so we don't have to interpret it because it wasn't strong enough. But weeks in release, we do have to do that one.
You highlighted, right?
Yeah, I kind of just like graded out. But um, then okay, so how about weeks in release? 4.54. What does that tell us?
If we skip opening row cells, no?
Well, that's the effect. So what's the cause? The cause, so you want to start with this. So if,
Early.
yeah,
We just go for it.
yeah, right,
No.
yeah,
That was the thing that initially.
right.
Whatever those values. That's why it's stupid increase opening those cells. And then the number of theaters one we didn't do, but if one theater.
Oh, yeah, right. Yeah. So basically, each additional week that the movie was in release increased, no spelling errors, increased total gross sales by 4.54 million. Okay, so each additional week that the movie was in release increased total gross sales by 4.54 million. There we go.
Like the movie company, like looking at this right here, and you're like, oh, like, that
Ye-
return would be.
Yeah, just keep it in for more weeks, right? Now that doesn't cover there might be costs associated with that. And maybe this is, or maybe they just want to be like, okay, we should boom our opening gross sales. Yeah,
Be like,
yeah. So I think most movies make most of the money like right away. I'm not, at least they used to. I think like the first month is like everything, and then everything else is just like for the fans. But maybe that's not true. Yeah. Okay. So it's pretty similar to what we did last time. The only difference is there's more checks for significance, and you really got to focus on the units and what I think this is the part where it's the most challenging, right? Part D. Yeah. So I kind of recommend like when you're doing this, when you get to part D, maybe just like I should have done this before, but maybe just list the variables and their definitions before. So for example, like let's just let's say we're doing part D for number one. All right, let's say that y variable equals, what is this? Amount charged. Okay, which is equal to amount charged in thousands or dollars. I think it was dollars. Dollars. Okay, so amount charged in dollars. Okay, so you know that all the coefficients that affect the y variable are going to be the effect in dollars, right? So y variable is amount charged, and that's amount charged in dollars. Well, this I went back to the other one first, right? Yeah, well, yes, for that one, yes. Okay, so y variable is amount charged, and that's amount charged in dollars. One of the, like, let's say x1 equals uh, income, but this was income in thousands. Okay, income in thousands. And then household size is just x2 was household size, which was the uh, number of persons in the household. Okay, so like number of people. So then, if you define those first, that would be a little bit easier. Like when you see the 33, you know that this is going to be like if the household increases, I mean, if the income increases by 1,000, then this is the effect on amount charged in dollars. If the household size goes up by one person, then this is the effect on uh, amount charged in dollars. So if you define like the y variable and the x variables and write out the units, then it'd be a little bit easier to kind of refer back. And so, so I'll put this here as a reference. Okay, and then if I did it for the other one, just to, for part T, okay, we would know that uh, the y variable was total gross sales in millions of dollars, right? Um, x1 was opening gross sales in millions. X2 was number of theaters, even though it wasn't significant, just number of theaters, and that's just, number of them. And X3 was weeks in release, and that's just measured in weeks. Okay, so then you know that like if you're doing this one, it's 1 million, one theater, 1 week, and the effect of the coefficient is always this amount. Yeah. Oh no. Annotate. How do I get out of this? Okay. All right. So, similar to what we did last time, but a few more steps and checks, stuff like that. This? No. No, you don't have to. Yeah. If it's helpful, sure. If not, no. Okay. Um, Questions on those? All right. Well, I'll leave you at least one to do, but I'll just pull it up to. So cost regression 2 is the other one. So this one, you're looking at total cost in dollars, and then the units are like the number of units produced. So if you look at the example, number 3, use cost regression 2, and run a multiple regression where total cost is assumed to be a linear function of units A, units B, and units C, and then do the same kind of analysis. So the only thing that you really have to know to specify is this is total cost in dollars. Okay. And these are just different types of products. So this is like total number of units A produced, or sorry, total cost of unit A. Wait a minute. What is this? Units A, units B, and units C. Oh yeah, this is how many, sorry. So units A would be like uh, total number of units of, let me do this in a different spot. Or like produced in the factory. You know what I mean? Like, here, so if I were to define them, like total cost equals just the cost in dollars. Okay. Um, Units A would be equal to total number of units of product A produced in month. Okay. And then units B would be total number of units B produced in the month. And then the same for unit C. Oops, that's a B, and that's a C. Okay, So total cost is just the cost of the business in dollars. This is each, so don't run month is anything, that's just when it was. So ignore month when you do the analysis. Oh, you did month? It's specified. But, yeah, that's okay. It's okay. So don't run the analysis with month. Run it where total cost is a function of units A, units B, and units C. And total cost is the cost in dollars. Units A equals total number of units of product A produced in the month. Units B is the total cost of units of product B produced in a month. And unit C is the total cost of units of product C produced in the month. So you're looking at basically the average cost per unit of different types of product. So make sure you focus on these things or these units when you do the interpretation. Okay, and I'll put that in the this part.
Again, the question is, they said you may have to do it, but I want to do it for
Uh-huh.
those mathy thing you're doing, like, so I didn't get that.
This part?
Yeah. Instead of like is that like B squared? Or like a little icon?
Oh, yeah. So you just under Home tab, there's a little see the little X2 button where there's like an X with a 2 below it.
Oh,
Subscript.
okay, got it.
Yeah, just hit that.
Okay.
Then you press and then type.
Okay.
In this one, scroll over to the Y.
Total cost is the Y, yeah. That's right. And then this is like X1. This is X2, this is X3. So if I were to just do what I did before, okay, so Y equals total cost in dollars. X1 is units A, and that's total number of units of product A produced in that month. And X2, units B,
Now you were like say you did have all this type, you do it full size.
and X3,
If you just highlight the one, press the code. That's just like I was hovering over that. What that is, what is that? Or so you see like pretty much
yeah, all the shortcuts are,
you wanted to look like how control and but that's like thanks for that is
all right. Questions on this? I mean, you really have to do just one more and do the do the estimate, write the equation, do the R squared, test for significance, and then do the yeah, do this part. Okay, and then there's a couple sections to read for in this part. Oops. Where did I put this? Week 3? Yeah, week 3, intro to linear regression. One point, which one was it? No, 2.1 and 3.1. It's only a few pages. Yeah, that's the book. You don't like it? Yeah. Okay, so everybody can do part 3, question 3, I think. And this shouldn't take too long. I know you have other homeworks. I'll try to get the other homework graded by next time, so you can at least have something up in your grade. And then this is due next week. And I think that's about it. We can. Sound good? Okay. All right. Any questions from Christina, Jordan, Michael?
Nothing here.
Okay. All right.
No, not at this time.
Okay, great. All right, I'm gonna stop the recording, but this should be that same link that I've sent out. It's also on Blackboard. So on Blackboard, there's like the YouTube page. If you click on that, so I'll keep adding them to this. So I won't. I'm not gonna send an email every time anymore, but so it should be available like tomorrow or whenever I get it. Okay. So all right, thanks, and I'll see everyone next Saturday.
You want me to know if I'm just gonna pause those? I don't-
No, I'm okay. Thank you.
No.